Hi everybody, Dr. White back again, continuing with our treatment of power series. I want to start again on the example where I had such a big typo that I felt I should not go through with it. I've corrected that typo, let's go again. So look at this power series here. It's only got even powers. You can see here from the x to the 2 to the n, but it's no less a power series anyway. I mean, it could be thought of as the x squared raised to the power n. So it's a power series, except the variable is like an x squared instead of an x. So we'll still go ahead and analyze this power series using the ratio test, okay? So we set up the n plus first term over the nth, absolute value of that, get ready to take the limit, work the absolute value signs as much as we can into the expression. On the top, we're going to have, when we put in an n plus 1, wherever you see an n, you're going to have a 2 times n plus 1 for that power, okay? And you're going to have a 2 times n plus 1 that you need to take the factorial of. The bottom is just the nth term. Okay, working the absolute value signs inside, the factorials are positive, so we can just leave them alone. But the x could be positive or negative, so I'm looking at the absolute value of x to the 2 times n plus 1. Similar thing down here. All right, rearrange like we know how to do. We'll come up with this expression here. Now, the reason we come up with this, or the reason we come up with this on the top, is that 2 times n plus 1 is 2n plus 2. On the bottom, we've got this factorial, again, because 2 times n plus 1 is 2n plus 2. Okay, now stare at this and see what will cancel. For this, you can see how there's going to be an extra 2 absolute value of x's left on the top. On the bottom, you're going to need to analyze your 2n plus 2 factorial. That's 2n plus 2 times all the numbers less than it. So it's 2n plus 2 times 2n plus 1 times all the numbers less than that. So I can really factor it as 2n plus 2 times 2n plus 1 times 2n factorial. And now I get a bunch of cancellation with the top. I'm left with this. Well, the limit of that as n goes to infinity will have to be 0. The top stays like it is. The bottom gets big. The limit will be 0. So this time, the radius of convergence is infinity. The series converges for all x. You might be curious, like, what does it converge to? And actually, we will learn what it converges to before the end of this course. You've probably been thinking, hey, I've kind of seen power series before, because like I've seen geometric series and they're like powers of things. And that's exactly right. You know, a geometric series, like some n goes from 0 to infinity of just like a, constant a, times x to the n, that is a power series. The sequence of coefficients is just always the same. It's the number a, and the center is 0. Now there's a special power series, there's a special geometric series, this one right here, where the constant a is a 1. And that one, you could write out the first few terms like this. That one is going to have to converge to 1 over 1 minus the ratio for all situations where the absolute value of the ratio is less than 1. So let's just keep this one in mind. It turns out you can relate a lot of things to it. So let me show you what I mean with some applications that bring in that special power series up here. Suppose you had to find a power series expansion for this very simple little fraction. Could you write that as a power series? Well, I can take 1 over 1 plus 3x and think of it as 1 minus negative 3x. But that can be thought of as constant over 1 minus a ratio in a geometric series, where the constant is a 1 and the ratio is the minus 3x. And if I multiply this out a little bit, I could write that as minus 1 to the n, 3 to the n times x to the n. And so, wow, we've got this as a power series. Now, that equation, this equals this, doesn't hold for all x's. It only holds for the x's where the power series converges. And so the absolute value of your ratio needs to be less than 1, which is the same as saying 3 times the absolute value of x has to be less than 1. So the absolute value of x has to be less than a third. X has to be between minus a third and a third in order for this fraction to be equal to this power series. Find a power series expansion for that fraction. Well, I'm going to proceed the same way. I'm going to try to get it as 1 over 1 minus something. Right now there's a 3 kind of sitting in the way here, so I just factor a 3 out from the denominator, and I'm left with a 1 minus x squared over 3 in the denominator. Well, that can be my ratio term. I can think of this as just 1/3 times this geometric series. Sum n goes from 0 to infinity, x squared over 3 to the n, ratio to the n. And then I can kind of multiply this out a little bit and have an x to the 2n on the top and a 3 to the n on the bottom. And I can push the 3 back in the denominator, distribute that back in if I want. And I've got the sum n goes from 0 to infinity, x to the 2n over 3 to the n plus 1. So this fraction is equal to this series. Well, it's not always equal to the series. It's only equal to the series when the geometric series converges. So that ratio term of x squared over 3, it has to be less than 1 in absolute value. Well, x squared over 3 is always positive, so I can just drop the absolute values. Looking for the x here, x squared has got to be less than 3. And so this equation works when the x's are between minus and plus the square root of 3. Then I can rewrite the fraction as that power series. But it gets even deeper. Could we find a power series expansion for tangent inverse of x? Well, tangent inverse of x is a function of x. Okay? I'll call it capital Fx. I'm just going to take the derivative of that function. You might think, why? Just follow along. You'll see. I'm going to take the derivative. And so f prime of x is, well, derivative of inverse tangent is 1 over 1 plus x squared. Oh, that's 1 over 1 minus x squared. I can write that as the sum of a geometric series, where the ratio term is minus x squared. And then I could kind of multiply out a little bit. That's the same as a minus 1 to the n times an x squared to the n, which is an x to the 2n. Add it up from 0 to infinity. Let me write out the first few terms of that. When n is 0, I'm just going to get a 1. When n is 1, I'm going to get a minus x squared, and then I'll get a plus x to the 4th, and a minus x to the 6th, and a plus, and so on forever. So this thing here, this power series, is the derivative of the inverse tangent. So let me take the antiderivative of it, okay? Now, this is a sum, and so you kind of think, well, the antiderivative of a sum is sum of antiderivatives. Now, this is an infinite sum, and there's not really a rule there that says that the antiderivative of an infinite sum is the infinite sum of their antiderivatives. Not really. But it is proved in advanced math courses that when you're looking at a power series in the places where it converges absolutely, it is true that the antiderivative of a sum is the sum of the antiderivatives, even though it's an infinite sum. So I'm going to do that. I'm going to think about the x's, just the places where we have convergence here. And I go up, and I think antiderivative of 1 is x, all righty. Antiderivative of minus x squared is a minus x cubed over 3. Antiderivative of x to the 4 is an x to the 5th over 5. Antiderivative of minus x to the 6 is a minus x to the 7 over 7. And I'm just going to keep on going with that pattern. In fact, I could write that pattern out like this as a summation. The minus 1 to the n, when you start with n as 0, it's going to give us a 1, and then a minus 1, and then a plus 1. It'll give us that alternation that we see here. And we have these powers of x, and they're all odd powers. And if I think of x to the 2n plus 1, when I start with n as 0, I'll get an x to the 1, just like I see here. When I let n be 1, I'll get that x to the 3, and so on. And I can also use that 2n plus 1 to account for what I see in the denominators. Because here I can think of a denominator of just x over 1. I can think of the denominator being 1. And when n is 0, I do get a 1 down here. But then I move to my 3 and my 5, and so on as the n increases. So it took a little thinking, but you can actually write that infinite series in summation form like this. So let's think about what we've got so far going on. We have this function, and we wanted to find a power series for it. We took the derivative of that function, and we found a power series for the derivative. We took the antiderivative of the derivative. And so you might think, whoa, we're definitely done. This is equal to this, you know? But not quite. Because actually all we know for sure is that tangent inverse of x is one of the antiderivatives, you know, of this function here, you know? So really, I should say to myself, tangent inverse of x is equal to that power series plus some arbitrary constant that I need to figure out. I also need to remind myself that that equality only works where the ratio that we looked at here, where that ratio in the geometric series is less than 1. So it only works when the absolute value of minus x squared is less than 1, which is to say that x squared is less than 1, which is to say that x is between minus 1 and 1. That being said, let's see if we can find what c is. Well, I know some things about tangent inverse of x. I know that tangent inverse of 0 is 0. The angle whose tangent is 0 is 0 radians. So if I use that fact, then like if I put in x is 0 here, I'll get a 0. And if I put in x is 0 here, I'll get some simple stuff. So I got 0 on the left, and I got the infinite series there where the x is 0, and I got my plus c hanging around. Well, that whole infinite series is just a bunch of zeros, so it's 0. And so I get the equation c is 0. So now I can say it for sure. Inverse tangent of x really is that power series that I got by taking the antiderivative of the derivative. So the beauty of this procedure was that this is hard to see how it could be a power series, but its derivative could be related to that special geometric series, and then you get a power series for the derivative. Take the antiderivative and you're just integrating each of the terms. Now you've got a power series for your original function. That's really useful because, like, I don't know any like quick ways to like find out what the inverse tangent of an arbitrary angle is. You know, I only know inverse tangents for very special angles like 0 or pi over 4. I'm sorry, 1. You know, like the inverse tangent of pi over 4 would be 1. I know inverse tangent for, you know, a few values. What if I needed other values? Well, what I could do is I could say, well, inverse tangent is as long as the x is between -1 and 1, the inverse tangent is equal to that sum. And so then I could use like a partial sum. Like I could just go out maybe that far with my x and add that up, and then I would have an approximation. So power series are really quite powerful that way. If you can express something as a power series, then you can approximate that things by looking at partial sums of the power series. That's a powerful idea that we will continue to explore in the next couple of sections. The other way around is often very useful. Sometimes you'll be doing some math, trying to find some quantity, and you'll find that your quantity can be written as a power series. But you would like to be able to just have a closed form expression for it. That means an expression that doesn't have like an infinite sum in it. So like say you got f of x is this power series, and you want a closed form expression for it. Then take this series, and I should have like a plus ... right after the 4x cubed, to indicate that it's going on forever. So let me write that in. Okay. And let's take its antiderivative. So I'll just take the antiderivative of each term. Antiderivative of 1 is x. Antiderivative of 2x is x squared. This has an antiderivative of x cubed, and so forth. Okay. So when I write that out in sum form, I could write it as the sum of x to the n going from 1 to infinity. That is almost the standard form for geometric series. What I could do is write sum n goes from 0 to infinity, and then just subtract off. Oh, there's a big typo there. That is such a big typo. That is such a big typo that I am going to quit and do this example. Wow, big typo. I'll finish this example in the next screencast, which is going to be very short. This is like the last example I wanted to do. See you soon.